Hello, this is the second video lecture for apportionment. If you remember in the first lecture, we talked about what apportionment was, and we did an example of Hamilton's method. And in this video, we're going to do Jefferson's method and perhaps the next one, which I can't remember the name of right now. So if you recall Hamilton's method, let's just take a look at review. If you remember that one, right, we found a number called the divisor, which basically tells us how many people each representative should be representing, right? And then you divide each state's population by that divider, which basically tells you how many representatives that state should have. And that number is called the quota, but recall that that quota is almost always has a decimal portion, and we can't assign a decimal portion of a person, right? So in Hamilton's method, you just dropped all those decimal parts and added up the whole number parts. And if you weren't at the number of representatives yet, you just started assigning representatives to the states with the largest decimal portion until everything was assigned, right? Pretty straightforward. Jefferson's method is similar. It starts out exactly the same way. But what it does once you find the quotas is different than Hamilton's method. And you'll find that that's really the main difference of all of these. You always find the quotas, and then the methods differ in how you then apportion based on those quotas. Okay. So if you remember, Hamilton's method always obeyed the quota rule. Like if using Hamilton's method, no state was going to get more or less than within one of its quota, right? It was either going to get its lower quota, which was its quota with a decimal part away, or one more than that. So that's nice. Jefferson's method acts a little differently. So we can look at, it says here, if you look at right here, kind of tells you a little bit about the method. But let's maybe, if I remember, we'll talk about that next time. Not next time. What am I thinking again? After we do it, right? Because I mean, it says here the method favors larger states. It's like, okay, but I don't really, like, in my mind, I'm like, why does it favor larger states? I think once we do the method, it'll be clearer why it favors larger states, right? And it does tell us here that it's not guaranteed to follow the quota rule, and I think we'll see that clearly once we do the method. My pen seems to be, look at that. Can you see that? Oh yeah, when I do a line, then it moves. That is weird. Huh. I wonder if I should restart. We'll see. If it's too big of a problem, I'll pause and restart. So of course, right, we should Jefferson is a name that's familiar to most of us, right? It's Thomas Jefferson proposed this method after President Washington vetoed Hamilton's method, and Jefferson's method was adopted and used in Congress from 1791 to 1842. So that's a long time. Okay, so how does Jefferson's method work, right? So you start the same way you did with Hamilton's method. You take you determine how many people each representative should represent by taking the total population of all the states and dividing by the total number of representatives. Now, instead of calling this number the divisor, they're calling it the standard divisor. And there's a good reason for that, because in this method, later on, you might have to adjust that divisor. So this number that they're calling the standard divisor might not end up being the divisor you use for apportionment. And so to indicate that, they've given it a different name. And then if you have to adjust it, then you can call that adjusted divisor down here, the adjusted divisor, or sometimes the modified divisor. I learned the modified divisor, so I probably will use that word. Okay, but it's the same process. They're calling it the standard divisor versus the divisor, but the process is the same. Total population divided by total number of representatives, which gives you people per representative, right? Okay, then you find the quota, just like before. So you take each state's population, divide it by that standard divisor, and that is the quota, which is probably going to be a decimal, right? All right, so here is then the third part actually is exactly the same as Hamilton's method too, right? You find the lower quotas. Oh, sorry, I forgot to silence my phone. There we go. You'd find the lower quotas. So basically you just, look at the whole number part, ignoring for a moment the decimal part. and then add up the whole numbers and then see how many you have, right? And remember that that answer, that when you forget the decimal parts and you add those lower quotas up, the number you get is always going to be either less than or equal to the number of representatives, right? If it happens to be equal to already, you're done and you don't have to do anything more. But typically it's going to be less than. So you're going to have some representatives that haven't been apportioned yet. Okay. All right. So here is where Jefferson's method differs from Hamilton's method. So if the total you get from step 3 is less than the total number of representatives, then you actually change the divisor. So you change the divisor and recalculate the quota. So let's see, how do you calculate the quota, right? You take the state's population. Oh, trying to write with a, you take a state's, oh my gosh, this is driving me crazy. All right, I think I'm going to restart my computer to see if that will stop happening. I mean, I guess it's not too bad. I'll see if I can live with it. State's population divided by the standard divisor. Right, and so you're going to get a number, right? So and this is just going to be some number. I don't know what it is, right? But notice that, like, if you add up all those numbers, right, from every state, and you get a number that's too small, right, how do you make the numbers bigger? That's what you have to do, right? Because you want to add them all up, because in Jefferson's method, you keep adding the lower quotas until you get what you want, right? And so you have to change the quotas. So the lower quota might change when you change the divisor. But the question is, like, if you have a fraction, right, and you change the number you're dividing by, right, how does that change the value of the whole number? So let's just do a couple of quick examples over here. Like, say, like, I don't know, let's make the top number, oh, I want a thicker pen. Imagine we have a fraction. The top number is 100, say, and say the bottom number was 20, right? So you do 100 divided by 20 and you get 5, right? Okay, so what happens if you increase the divisor? So that's the number on the bottom. If you make that number bigger, what happens to the result, right? Does the result get smaller or does it get bigger? Let's try it. Let's just say, what if we do, instead of 20, let's do 25. So notice that we have taken the divisor and made it bigger, right? So we're dividing by a larger number, and 25 goes into 100 4 times. Okay, that's less than 5. So you can see if you make the divisor bigger, the number actually gets smaller. Okay, so if you need to make your quotas bigger, you can't make your divisor bigger, right? Making your divisor bigger is going to shrink your quotas, right? So we can, if you just look at it in the opposite direction, right? If you just start looking here, if your divisor was 25, if you decrease your divisor, you increase the quota. You see what I'm saying? So if you start with 25 and you get a quota of 4, right? Well, if you want to make it bigger, you have to decrease, right? So decrease divisor to increase the quota. Oh, yeah. I guess I should have started that way, because we know that the total from step 3 is always going to be less than or equal to. So if it's less than total representatives, we need to allocate more, right? So if you want the quotas to be larger, you have to decrease your divisor. So it's very easy to think separately, right? Because one thing is getting smaller, the other thing is getting bigger. So you have to have that in your mind. Okay, so that's what step 4 tells us, right? If the total from step 3 is less than the total number of representatives, you have to reduce the divisor. Reduce the divisor, make it smaller, and then recalculate the quota, and then find the lower quotas and allocate again, right? So notice, like, this is very different from Hamilton's method, because in Hamilton's method, once you found your divisor, it was your divisor all around. Now, if the standard divisor doesn't work, we're going to reduce it until we get one that does work. And you might have to reduce it multiple times, okay? Because you're going to continue doing this until the lower quotas equal the number of representatives. and that the modified divisor you end up using, or the divisor you end up using is called the modified divisor, or called the adjusted divisor. I prefer the term modified divisor, like I said. Okay, so let's apply this idea to the example. We're actually going to use the exact same situation as we used for Hamilton, right? Same 5 states, small country with 5 states, same populations for each state. But we're going to use Jefferson's method to allocate these seats as opposed to Hamilton's method. Okay, and I do want to say, like, I didn't do this example by myself before I made this video, and I did that on purpose because I like to sort of I want it to be kind of fresh, you know what I mean? Like you haven't seen it before. So when you try and do this, you're going to be coming at it with like a fresh mind. And so I kind of want to do that too, so I can sort of model, right? I mean, maybe I'll make some mistakes and you'll see how I deal with those mistakes. And then you'll see if I find any flaws in my thinking. Probably some of you are making those same flaws, right? So I kind of like it to be, I'm trying to simulate sort of how it is for a student. So since it's been a while since I've done these, I feel it's like fresh in my mind. Okay, so let's see if we can do it. So we have a small country with 5 states with the populations, and these are the same populations as before. All right, so what's step 1? Let's go back here. Step 1 is, we have to find the standard divisor. So we take the total population and divide it by the total number of representatives. So remember, we have 119 seats to allocate, and then these are our populations, so we have to add them all up. Since those are the same populations as the example we did in the previous video, the total population is going to be the same. So I'm just going to take that number, right? Because notice they're the same. 810, 473, 292, 594, 211. 810, 473, 292, 592, same population, right? So the total is, what was it? 2,380,000. 2,380,000. Okay. And actually, the standard divisor is going to be the same, because then you're going to take that total and divide it by 119, which we did in the previous example anyway, right? So I'm going to call the standard divisor SD, S for standard, D for divisor. So we take the total population, which is 2,380,000, and divide it by the number of seats, which is 119. And if you recall, that was 20,000. So let's just show you here. Right, we did that. So now the standard divisor is 20,000. Now we might not end up using that divisor if that doesn't work. Okay, and I think the other calculations, even though we did them, well, see, no, we did all those calculations. We found the quotas in the previous example, so I don't want to redo all that work, right? I've already done it. I've taken the 810,000. I mean, 810, oh yeah, 810,000 divided by 20,000. I've done all that. So let's just copy these quotas, right? These are the same quotas because the math is exactly the same. We have the same population with the same divisor. And so I'm just going to write them down, right? Let's see. I actually might end up, instead of scrolling back and forth, I might just do the math real quick on my calculator so I don't have to keep scrolling back and forth, because I'm not going to remember them all. Okay, so let's see the quotas. We want to list the quotas here. Quotas. Okay, for state A, remember that was 810,000 divided by 20,000, 40.5. Yes, I just realized that I could chop off the same number of zeros of each number and not have to plug in the zeros to my calculator. So the quota for state A was 40.5. The quota for state B was 23.65. The quota for state C was 14.6. For state D was 29.7, and for state E it was 10.55. All right, just gonna look. Yeah, okay. Hey, wait, I have a different one. Why did I get, for C I have 13.1. Did I have 13.1 here? Why did I have 14.6? Does that mean I did it wrong last time? 292,000 divided by 2,000. That's 14.6. Huh. Dang it. So that means there is an error in my last video. Okay, so I don't know how I got 13.1. Let's see, is my calculator stuff still there? No, that's too far back. Well, I don't know. That's a lot of stuff. Okay, so that was an error. That was an error on that part. Oh man, I wonder if I should redo that video. I'll post an announcement and see what people think. Did it affect the allocation? Possibly. Especially since the decimal part was 0.6 as opposed to 0.1, which is a big difference. So yes, it would have affected it. So I will probably do a correction. I'll redo that and post it later. But let's do Jefferson's method now with the correct quotas. I bet somebody watched that video and they were like, that's that, and they could see my error as I plugged it into the calculator, but I don't know what it was. And then, wait a minute, I double checked those numbers and I still got, are the populations different? They're not different, right? Populations are the same. 292. Huh. Oh, you know what? 20,000 times 13.1 is 262. So I bet I typed in 262 in my calculator as opposed to 292. Okay, so there's my error. So I'll send out a message. I feel like I don't necessarily need to redo that example. I mean, everything else was correct except for that one number. Now, it is true that the allocation would be different. This allocation that we got where 41 went to A and 24 went to B, this allocation might actually be a little bit different. Like maybe C would have actually gotten one more and somebody else wouldn't have gotten one. So that is true. So that's a big deal, right? Yeah, so maybe I'll fix it. Okay. But let's focus now on Jefferson's method. You see, it happens, mistakes happen all the time. I didn't even catch that one, but there was nothing. Notice how there was nothing in this work. Like after making that error, and apparently I made it twice, because I thought I had checked that work, right? After making that error, there was nothing else in the work that I was doing that like could shed any light on that. You know, like sometimes, a lot of times in algebra, like if you do an error later on, you might see something that looks weird and then it might alert you to that error. But there's nothing else happening in this method that alerts me to that error. So like, you know, I mean, if that decimal number, if I use that as the decimal number, the rest of the method just works fine, right? There's nothing going on there. So the method was okay, but I had a computational error there, which is not good. Okay. So Jefferson's method. So now I have the actual quotas, right? You should double check, make sure that I did them, because I did them on my calculator again. And yes, they all seemed good. Okay, so what's step 2? So we got the quotas. So we have our standard divisor. We got the quotas. Okay, now we want the lower quotas. Now you could just like, I'm just going to like underline here, these whole number parts, those are the lower quotas, right? If I add them all up, what do we get? So that's, here, I can use my calculator here. Pay attention to my work, make sure I don't type in the wrong number. 40 plus 23 plus 14 plus, see, look at there, I did it again. I tried to hit the 9, I hit the 6, plus 29 plus 10. Now I know that's a thing I tend to do. Okay, so 10 plus 29 plus 14 plus 23 plus 40. Okay, that's 116, which is not quite 119, right? We're 3 away from the 119 that we actually need to allocate. Okay. So what do we do according to Jefferson's method? If the total from step 3 was less than the total number of representatives, then we are going to reduce the divisor, make the divisor smaller. Okay, what was the divisor? Our divisor was 20,000. Okay, we're going to make that number smaller, and we're going to recalculate. Okay. So I'm going to adjust my little title here, this quotas. I'm going to call this quotas with standard divisor. Okay, because then we're going to recalculate quotas with a modified divisor. So I'm going to say quotas with modified divisor, and I'm going to say modified divisor 1 because we might have to do it more than once. I don't know. All right, now you might be thinking, okay, but by how much should we reduce the divisor? Like, there's nothing to indicate how much you should do it. Well, if you take a look at the textbook, right, and look at what they do in all the examples, it's pretty common to maybe, like, if your divisor is, notice our divisor is 20,000, right? So it's kind of, you're thinking, we're thinking thousands, so maybe we'd reduce it, say, like by 500, right? Maybe not by a whole thousand, but by 500, and that's a pretty standard thing, right? I would say that, like, if your standard divisor was like in the millions, you might want to reduce it by 500,000, right? Or if your standard divisor was in just the thousands, say like it was like 3,000, maybe you would use like 50 or something, so it's very common to do sort of like, take like the order of magnitude that your units are in. So like 20,000, that's in the thousands. So half of 1,000 is 500. Right? If your numbers were more like in the hundreds, like I would say if the standard divisor were like 2,000, that's more like hundreds. So you would take like half of 100 or something. But really, you can play around with it, right? Like I'm going to kind of mimic what the book does. And when the standard divisors are about this size, they decrease by about 500. And see if that works. But as soon as you try something, you're going to see whether it is like in the ballpark or not, right? If you say you want to say, well, I'm going to reduce the standard divisor by half and use 10,000, you'll see that it's probably going to be way too small, right? And then you'll know that you'll have to adjust. So it's not like you have to know how much to reduce it by to do it, because as soon as you make any decision, you'll see how far off it's gone, right? And then you'll start adjusting upward from there. Like if you go too low, you'll see it because your quotas are going to be way too big. Does that make sense? Okay. Hopefully that made sense. So I might say modified divisor 1. Oh, we need to say what the modified divisor is. So let's call it, I don't know. We want to do, so that would be what? 15,500? Is that what I said? Reduce it by about 500, 15,000. What am I thinking? My brain. All right. I don't know. I just wanted all the fives, I guess. Yes. So if you take 20,000 and you minus 500, you get 19,500. But like I say, I encourage you, like, if you want to go lower, see what happens. I don't know what's going to happen with this divisor because I haven't done it. Let's see. All right. So now we have to find the modified quotas, right? Or did they call them modified quotas? No, but we do have modified quotas. Okay. So let's do it. So for state A, we're going to do, now you can watch me. So if I make an error, then you'll be able to see it on the calculator. And even if I don't see it, you'll be like, she made an error. Okay. So we're going to take state's A population, which is 810,000. Right. 810,000. And we're going to divide it by this new divisor, 19,500. Okay, so notice now it's 41.53 something. So I'm just going to write it out to 3 decimal places. That should be more than enough to do. That should be 3 decimal places is nice, right? I feel like 2 might be, I want to see more, because what if, especially if any 2 numbers end up agreeing in the first 2 decimal places, you definitely need to have a little bit more after that to see which one is actually bigger. So I'm going to write 41.538. I would do standard rounding, right? So since the number after the 8 is 4, that's less than 5, so the 8 stays as 8. Hey, quit it. Quit it. All right, B. The population for state B is 473,000 divided by the new standard divisor, 19,500. 24.256. So these 24.256. I'm noticing that, right, we've already increased our total, right? And we're talking about this total of the lower quotas by 2 because 40 has gone up to 41, 23 has gone up to 24. So our sum is already going to be 2 bigger. Okay. See? 292,000 divided by 19,500. 14.97. Okay, so notice how that lower quota is going to stay the same. 974. Because the 14 part is the same, so when we chop off the decimal, so that's not going to add 1. All right, D, population was 594,000. Divide that by 19,500. 30. There's another one. So we have another increase. Notice how we've already increased by 3. So if the fourth one, the last one increases also, we've actually got too much. So I'm rounding that to 0.462. Because if you look over here, that's 461. So if I want to round to the third decimal place, I look here, the 5, that's 5, so the 1 goes up to 2. It's always good to remind yourself about rounding because it's one of those things that's easy to forget how to do, especially if you never like really thought about what rounding is. Because if you really understand what rounding is, you don't have to memorize rules. It becomes clear because you're looking for, right, like 461, like this number, right? This number is between, it's, what am I trying to say this, right? You're trying to see, like, if you're adding here, you're adding fractions of something, right? And you're trying to say, like, well, which decimal place is, if you add 5 of the next order of 10, right? Because what I'm saying is, right, the 4 is in the 10th spot, the 6 is in the 100th spot, the 1 is in the 1,000th spot, and the 5 is in the 10,000th spot, right? So if you're trying to figure out, is this number closer to 1,000ths or 2,000ths? That's why you look at the next one. You say, okay, 5, am I closer now to the 2,000th spot or am I closer to the 1? And at 5, you're closer to the 2 because you've gone through all the 0s, 1s, 2s, 3s, 4s, and now once you hit the 5s, if you're over that, then if you're there or over, you're closer to the next one. So I don't know if that made any sense. All right, so state E, you get 211,000 divided by 19,500. 10, okay, so that one stays the same. 821. I round that third decimal place to 1. Okay, so I was kind of keeping track as we went, but I think these lower quotas are going to give us exactly what we want because we're going to get an extra one there, an extra one there, and an extra one there, and these 3 are going to stay the same, and that's 3 extra. So that should add up to 19. 119, let's just double check. 41 plus 24 plus 14 plus 30 plus 10. There you go. Okay, so then those lower quotas are the quotas that we want, and that with the modified adjuster of 19,500, that works. So let's list them, right? I should look in the book. I don't know how they list it in the book, but I'm just gonna write allocation. All right, so state A gets 41, state B gets 24, state C gets 14, state D gets 30, and state E gets 10. And that's the final allocation. We used the modified divisor of 19,500, and it worked. Now you may be asking, well, what if that didn't work? What if we made it too big and we actually ended up with 120 or 122 or something like that? Then you would have to adjust the divisor again. So notice, right, so we had decreased the divisor. If that had resulted in too many seats, right, then we would have to go back and increase the divisor a little bit. So if you look at these two numbers, right? So I'm talking hypothetically here, like 20,000 made the quotas too small, right? So we reduced that divisor, but then if that had made the quotas too big, then we would have to increase it a little bit, but not as much, not back up to 20,000. We'd have to find some number in between those two to see if that would work. Does that make sense? I was going to say, is there an example like that? No, but I think there's one in the book. I believe there's one in the book. Okay, so that is Jefferson's method with no errors, I think. Okay, I think I will end this video here. Maybe I'll make another video fixing the Hamilton's method I did with the fix my error. And then we'll come back and do the next one, which has a weird name. Oh, that's not so weird. Webster's method. Oh, it's the next one that has the weird. It's the Huntington Hill. That's the one that has the weird name. Okay. All right. So as always, or if you have any questions about any of this, make sure you reach out to me. And I'm always happy to hear from you. Okay. See you later.